So thanks very much for the introduction. And I did already speak on LC3 once this week, so I'm trying to change it around a bit and hopefully get to talk a little bit more about the science this time. So at the beginning, I always like to show this slide just to remind people we are not talking about a carbon-intensive material. Most journalists who contact me say, what are we going to do about this carbon-intensive material? But we don't have a carbon-intensive material. We have a problem simply because it's so successful. We use so much of cement in the form of concrete and mortars, which make up more than 30 billion tons of material every year. So because it's actually quite low carbon, it means it makes no sense to replace it with anything else, even though we can have things like timber, which can come under a heading of a lower carbon, depending on how you calculate the embodied carbon. We just don't have enough. If we wanted to replace just 1/4 of cementitious material with timber, we'd have to plant new forest 1.5 times of the size of India. And that would be a great idea, but even if we could do it tomorrow, we still have to wait 30 years for it to grow. So on the horizon of 2030 deadline, 2050 deadline, this cannot deliver more than it's doing already. So we're stuck with concrete, and it's a good product already, but we need to make it better. The second thing we always need to keep in mind is where cement and concrete are being used. And I'm sorry, it's not here in the USA. The developed countries of the global north collectively now make up only around 10% of cement use. The big game changer in the last 30, 40 years has been the growth in China, which now makes up more than half of production. But use in China is going to go down, and that's going to be taken up by the rest of the global south, India, Southeast Asia, Latin America, and most of all Africa. So we have to have solutions that can be used there. And here we should think about what influence we have, because the kind of codes and standards we develop in North America and in Europe are then used in many, many other countries around the world. So we have a responsibility not just for what we can do in the US, where production of cement only accounts for something like 1.5% of the CO2 emissions, but to influence other countries like Kenya, for example, where cement and concrete already makes up something like 20% of emissions. Now, I explained this on Sunday. If you want to know more, there's plenty of presentations I made online which go into the detail. But the fact we use what we call Portland cement is an inevitable consequence of the chemistry and geology of the earth. So, it's no good thinking that there's some wonder new cement out there we haven't discovered. We know that many, many technologies are limited by raw materials. I mean, electric batteries for cars are now limited by supplies of lithium and nickel. Electrolyzers everybody wants to use for green hydrogen, for example, are going to be limited by supplies of iridium. So we have to be realistic about what we can use to produce something we produce 30 billion tons of a year. And believe me, Portland cement is the best answer to that question. Now, that doesn't mean we can't do anything. We can do a lot, and what we can really do fast is to replace a considerable fraction of the clinker by supplementary cementitious materials. And I think this is one technology which was really underestimated in the GCCA roadmap. So this technology is not new. It's been around for a long time. Maybe 50 years ago, cements were just clinker and gypsum ground up together to produce cement. But in most parts of the world, we've been using SCMs for a long time. We've been using limestone, which just comes from the cement quarry, which finally is making inroads here in the US. We've been using fly ash, which has been added at the concrete level. But the problem with fly ash, it comes from burning coal. And that's the number one thing we have to do to confront climate change, because burning coal is accounting for something like 60% of CO2 emissions. And that's where we can move fast, by going away from coal. I mean, already one of the biggest factors in the reduction of CO2 in the US has been switching from coal to gas. Just doing that, still using fossil fuels, you can have huge reductions. Slag is coming from producing steel. And again, that's a very energy-intensive process, something like 10 times more energy-intensive than producing concrete. And even today, the amount of blast furnace slag we have available is just about 8% compared to the production of cement. And so even now, 95% of blast furnace slag is already used in cement and concrete. If you specify high slag levels in your project, you're just taking it away from another project. And globally, in terms of the world, which is what matters, you have no net reduction in CO2. And then people are looking at other slags, like steel slags, but the amounts of those are even smaller. Steel slags are typically about 2% of cement demand. So by all means, let's use these materials, but they can't take us much further than we are already. And then what we've got, which can really extend this technology, are clays, which is what I'm going to talk about. So this just shows what I already said. Slag, very limited supplies, already all used. Fly ash already quite limited and going to go down, but a very variable product, so it's quite difficult to use of all of it. Limestone we have a lot of, but when we go above levels of about 15%, we simply have a dilution, which doesn't really help anything. And then we've got clays that can be calcined. Now, we have to go further than that, because what is really interesting is this synergetic reaction between calcined clay and limestone. And this is the basis of the technology we call LC3, which stands for limestone calcined clay cement. And with this project, we've been supported the last 9 years by the Swiss government. Now we're supported by other organizations, notably Climate Works, who are here in the room, and we'd like to thank you for their funding. Now, the essence of this is that rather than just having only a pozzolanic substitution, such as we might substitute 20 or 30% material with the pozzolan, by exploiting this synergy between the calcined clay and the limestone, we can replace another 15% of the energy-intensive clinker with limestone, which has virtually zero CO2 emissions. And you have a whole family of this. What we usually talk about is LC350, where the amount of clinker is just 15%, but you can have higher amounts of clinker. You can also have much lower amounts of clinker. And this just, explains why we reduce CO2, because we replace the clinker by a combination of calcined clay and limestone. Limestone, virtually no CO2, and calcined clay, very low CO2, a little bit of CO2 from the fuel to calcine it, but this is about 10 times less than clinker, and eventually we can see this process being electrified. And the really interesting thing is with this combination, in as little as 7 days, we can reach the same strength as the reference Portland cement. So you've got the same strength really quite quickly. So in essence, we're talking about something with 50% less clinker, 40% less CO2, because we have a little bit of energy for the calcination, and we have a similar strength, and we have a very good performance in terms of durability, in terms of resistance to chloride penetration and alkali silica reaction, which are two of the major causes of poor concrete durability. So why can we get such high levels of substitution? It's because we use clays which contain some kaolin, and kaolin has this crystal structure like this. We have a layer of silicon atoms and a layer of alumina atoms. When this is calcined in the range 700 to 850, this structure gets disrupted, and the silica is available to react in the conventional pozzolanic reaction, but then the alumina can react with the limestone. And alumina reacts with the limestone to give these products called carboaluminates. These are already there in Portland limestone cement, so they're not something new, they're something we understand, and these contribute very well to strength and durability. Now, this is an interesting study we made where we compared calcined clay, slag, and fly ash, and then in binary blends with just 30%, and also in ternary blends where we have another 15% limestone. And if we look at the strength development here, we see that if we look in the very long term, all these blends do very well. But the big advantage of the calcined clay is that we develop the strength much earlier. And particularly, we have pretty comparable results between the binary blend with just 30% replacement and the ternary blend with 50% replacement. And, you know, these stay ahead of the reference at 7 days, whereas you see the limestone addition tends to have much more impact on the mixtures with slag and fly ash because the alumina in those materials is not so readily available. They're much more slow reacting materials. And of course, one of the main limitations is the strength development at early age. If you're producing these materials in a cement plant, you can optimize the particle size distribution of the clinker component, and you can get even the same strength at 1 day. And this doesn't negatively impact rheology. You have some impact of the calcined clay, which can be dealt with superplasticizers, but the grinding of the clinker doesn't make it any more difficult. And this is a nice comparison based on cements in Chile, which have used natural pozzolans, uncalcined pozzolans since the 1960s. And they have 2 cements on the market, one with 20% replacement, one with 35% replacement. And now if you go from a natural uncalcined pozzolan to calcined clay, you can match that performance at much, much lower clinker contents. You can match the performance of the high-strength blend, 80% clinker, with only 35% clinker, and the general use one with only 25% clinker. So this gives us an incredible potential to go to much lower CO2 contents, which we can't do with other SCMs. Now, as I've said before, we need some of this kaolinite, but the distribution of this kaolinitic clays are very widespread in the world. Everywhere you have this kind of orangey yellow color, you will have kaolinitic clays. And what's really exciting is we see that these materials are really available in those parts of the world where the use of cement is going to increase most. And these parts of the world, I mean, Africa, for example, apart from South Africa, there's no fly ash, there's virtually no slag. So they don't have SCMs there at the minute. Further than that, they don't actually have much limestone, so often they've got to import clinker, and being able to produce calcined clay locally can dramatically reduce their need for imports and therefore reduce the price of cement. We can quantify the kaolin very easily by looking at the weight loss in the range 400 to 600, and we can see that the strength development correlates very closely with this kaolinitic content, and the red bars here are the reference Portland cement. So if we want to have a similar strength of 7 and 28 days, we need a kaolinitic content of somewhere around 40%. But even some of these clays in the range down to 30 are doing pretty well. So we can calcine it very simply with existing technologies. We can even do production in an existing clinker kiln. We did a trial where just 6 hours after stopping producing clinker, exactly the same kiln could produce calcined clay. Now, obviously, you don't want to switch production around, so if you want to produce calcined clay on a regular basis, it helps to have a specific kiln, but this can be a rotary kiln or a flash calciner. And we've taken this through to full-scale building structures. This is a plant which was recently commissioned in the Ivory Coast, and what was particularly interesting in this plant was we could show that you can change the color of the clay. So many people said, well, people don't want to buy red cement. You can say, why not? It might even be a good marketing strategy. But if you don't want red cement, you don't have to have red cement. This doesn't at all affect the reactivity of the clay because it's just to do with the iron oxide impurities in the clay. So the potential of this is really phenomenal. This graph here shows the average level of clinker substitution around the world according to the GCCA figures, and you see for the last 10, 15 years this really hasn't moved at all. And the biggest substitutes today are limestone, slag, and then fly ash and a little bit of pozzolans. And the reason this hasn't moved is precisely the limitation in the supply of slag and fly ash, as I already pointed out. Now, if we remove this limitation by bringing calcined clays into the mix, we can easily go to a level of substitution of 40%. Nobody's really argued with me about that on average we could go to that average level of substitution, and that would represent a saving of 400 million tons of CO2 per year. To put that in context, that's 10 times the emissions of Switzerland, where I'm from. It's something like between 1% and 2% of the entire world emissions. But certainly on a horizon of 2050, I think we could do a lot better than that. You saw already we had good performance down to clinker contents of 25 and 35%. So we could probably do twice. I think we can definitely do twice as well as that. And that's a really significant contribution to world CO2 emissions. And what's even more interesting, we can actually do it at cheaper cost. So we're always hearing about green premium. We're always hearing that these new products cost more to make than the existing ones. But this study here, we evaluated it very closely, and even up to 200 kilometers from a plant, even if you have to bring your cement, your clay that far, you can, in an integrated plant where you're also producing clinker, have reductions of like 10, even 20%. In a grinding plant, which is the situation in most of Africa where you have to import clinker, you can have much bigger savings. And this study was done a couple of years ago before the energy crisis. As energy prices go up, these differences will increase. And fortunately, we can say we're now working with people in all these countries. This India, we already have the announcement that calcined clay will be used in this new building, in this new campus. Now, just to, for the second part, I'd like to sort of go a little bit more into the science to really explain to you why this is such a good material from a durability standpoint, as well from a low CO2 standpoint. And the two outstanding advantages are resistance to chloride penetration and suppression of alkali-silica reaction. So suppression of alkali-silica reaction, basically we have a pretty much flat line now. This was our results after 1.5 years in alkali solution. We now have results out to about 6 or 7 years, and we still see no expansion. And we know from a previous study we did earlier in 2012 that the presence of even very low concentrations of alumina in solution really suppresses the dissolution of the aggregates. So you're suppressing the reaction at source by the presence of alumina, stopping the silica dissolving. Chloride resistance, also outstanding. And these are the blends I showed you earlier, the binary and the ternary blends based on clay or slag or fly ash. And here is the reference Portland cement, very deep chloride penetration. Here are the slag blends, they're better, the fly ash better again, but the best of all are the calcined clay blends, and the best one is the combination of calcined clay plus limestone. And the effective diffusion coefficients of the calcined clay plus limestone are 10 times lower than the reference. Now, when we first started working on this, we thought it was all to do with the pore structure refinement. We can see the mercury intrusion porosymmetry curves for the calcined clay mixtures have much finer pore sizes than those for the Portland cement. And even by transmission electron microscopy, we can see this very dense structure given by the CSH. In fact, when we studied these 6 blends in more detail, we see it's really rather difficult to draw conclusions, because here we looked at porosity versus transport, both in terms of total porosity and the critical pore size, and we see no particular correlation between them. Many people say, well, it's all down to binding, and binding's rather complex because, yes, you form more carboaluminates which combine chlorides, but on the counterpart, you've got less CSH, so that's less chlorides. So if you look at the concentration we have in seawater, which is really what we're talking about, you see most of these blends don't have much difference in their binding capacity. The one that has the highest was just the calcined clay on its own in the binary blend, but in fact we see that that didn't have the best performance. And this is the overall correlation. Again, you can see no particular interest. And so we got something missing. Well, what's missing, and what's probably missing, is the concentration of the pore solution. We can see there's a very nice correlation between apparent diffusion coefficient and the sodium potassium in the pore solution. And I would like to point out that even though we lower the sodium potassium in the pore solution, we're still well above pH 13, so no problem for protection of reinforcement. And then when we studied a wider range where we looked at the impact of water-cement ratio, and we studied it in this new mini migration test, looking at the flow of chloride through these paste samples, what's really interesting is we see that all the calcined clay blends, so even the calcined clay at a water-cement ratio of 0.5 is better than the Portland cement even at a water-cement ratio of 0.3. So of course we know water-cement ratio is important, but we've got impact in the calcined clay way beyond that. And we looked and we said, well, is this related to the porosity? We calculated the porosity by the free water by freeze drying. We see no particular difference. If anything, the LC3 has higher porosity. We then did a detailed study by proton NMR. Again, we see if anything, the calcined clay has got higher porosity. So why does it have lower chloride diffusion? And then we calculated this thing people call tortuosity. And I'm going to tell you, well, you know, we have this idea tortuosity is pore complexity, but it's really not the whole answer. And we see these very nice high tortuosities, but as I want to stress, you know, the term tortuosity is misleading. We think of it as being, you know, well, the iron has to go through this complex pore path, and to get these very high tortuosities in the range of 100, well, you'd have to have an incredibly tortuous pore path, but you really can't produce that in a statistically isotropic material because you have another tortuous path like that, and you can always find a shortcut through here. So the problem is that the way we define that, it's really just a ratio of conductivities, which is covering many different effects. And we've looked at this in more detail. What's particularly important is the fact that in practical materials, we've got relative humidities which go down quite significantly. So we're not at 100% relative humidity, and this means most of the pores are empty. You can see here in these long-term experiments that after 3 years, the radius of pores that can still contain water is only 5 nanometers. And in those 5 nanometers pores, you have a very complex interaction of the ions with the CSH surface. We've tried to model this in this recent thesis, and basically we see that there are several factors interacting. So we've got the pore size effect, we've got the fact that the CSH surface changes, and we've got the fact that the pH of the pore solution changes. And so we've got 2 times 2 times 2. I know that equals 8, but, you know, our model isn't perfect yet, so that's roughly equal to the 10 times reduction we see in practice. So all of this is really to demonstrate that we really have a very sound understanding to be sure that we have good durability of these blended cements with calcined clay. And after all, the kind of products we're forming are exactly the same products that we have in existing cements we've already been using for the last few decades. Now, just to finish, I want to, you know, stress that this isn't the end of the story. Calcined clay gives you a huge potential for CO2 reduction, but you should never see it in isolation because we have to work through all these steps of the value chain. Reducing CO2 from clinker production has already been largely achieved. The quick wins have been implemented. We can still go somewhat further by having efficient plants, using alternative fuels and raw materials. In the clinker and the cement, we can go further by increasing the amounts of SCMs, which is really only possible by using calcined clays because slag and fly ash are already used up. But we then have to take it further by making sure that we produce concrete efficiently. And that's usually as simple as using good aggregate grazings, using good admixtures. These are things that have been around for a long time, but they're often forgotten. And we see concretes out there that have 2 or 3 times the amount of cement they need to have. 2 or 3 times the amount of cement means 2 or 3 times the amount of CO2. And then we've still got to work on reducing concrete in a building. The problem is that concrete costs much less than an engineer's time. So it's usually more expensive to say, well, how do I optimize my building to make sure I'm not over-designing? And we have a kind of, overdeveloped safety reflex. We have codes which already have very good safety factors, but then people say, well, maybe I just had another 10 or 20% just to be on the ultra safe side. We now have to think that adding 10 or 20% is adding 10 or 20% more CO2, and we have to stop using it. And finally, we need to think about how we use buildings. Do we really need to demolish a building and build a new one, or can we reuse what's already there? Because that's certainly going to save you more CO2 than anything. So we have to bring all these steps together, and if we do that, our estimates are we can achieve 80% of reduction of CO2 from cement and concrete. And basically it comes down to this. We've got all these steps, efficiency in design, efficiency in concrete, savings in cement and binder, which can be achieved at very low cost. And then at the end of the day, you've got something left over, which has to be dealt with by carbon capture and storage. Now, in the GCCA roadmap, they had 36% here. If you even have 36% going to carbon capture and storage, that is going to increase the price of your cement by a factor of 2 or 3. So it's your choice. Do you want to pay 2 or 3 times more for your cement, or do you want to work on these steps and save yourself money? I think it's, maybe there are teething problems, there are difficulties to be overcome, but we have a lot of benefits for really trying to maximize these levers here and minimize this one down there. And that's without talking about the extreme difficulties of implementing these carbon capture and storage technologies in these developing countries. So coming to the conclusion, I hope I've convinced you that we can do a lot about concrete. It's not just about calcined clay, that's one possibility, but we have to make sure that's part of an integrated package, working on concrete and working on structures. And we have to get the different parts of the industry working together. And all of these can lead to lower costs. We're going to have some carbon capture and storage, but this will be high cost and the infrastructure is not yet in place. And, when we come back to the SCMs, we won't have more fly ash and slag on a worldwide basis. You can say, okay, we can dig fly ash out of the ground, that's fine, but that's going to be a short-term solution, and we need to think long-term here. And putting calcined clays into practice, the big advantage, we're not limited by raw materials. All the technology is existing. We already have something like 10 plants around the world producing this stuff. So there's really no reason we can't roll it out at large scale and very fast to meet our objectives by 2030. And with that, I'd like to thank you for your attention.